y'all? Darrell Lee Berry Jr. back for some more physics, science, math, all that good stuff. I apologize for being a bit late. My last stream ran over a bit. I was basically in the last stream just now calculating the Hermite polynomials for solutions to the quantum harmonic oscillator, which is something I'll be doing a lot of, at least the next level, a lot of in my quantum 2 class. Right now we're doing perturbations of quantum states. And in order to properly do perturbations, you have to. Lisa says, "Don't cross the streams." Yes, I've been in a lot more streams. As promised, I've been focusing on the science and the math, uh, uh, in implementing, covering the things I'm covering in class more. So that's definitely been fun. And I've been preparing for the reason why I want to make sure to get at least so far in my quantum is because I'm hosting a study group tomorrow on that topic. So I want to make sure I got through it. So those who've been watching my streams for a while, y'all familiar with my notes. I have some notes together and stuff. So a lot of times it's pretty much how I do my study groups as well. So I'll be doing a study group on that. I think I got far enough. But I know I'm going to do this stream, and I know that Nicholas may show up. He may or may not. This guy that was in the stream yesterday spewing a bunch of stuff in the live comments, but as said in the past in my farewell to Dirt video, that if somebody does seem sincere, I don't mind talking to them. So I have him on to talk to him for a bit, but if he shows, but it'll be a short. I won't give him so much time to actually show he knows what he's talking about, which I mean it seems clear he doesn't, but I'm open to being proven wrong. And if he doesn't show, I think I'm just going to just mute him on the channel so that we don't have people disturbing our discussions with a bunch of nonsense and then run away. At least I say it's Flat the Fatter and Drunk Debunk Show are doing concurrent streams to derp his mind numbing. I need some intelligent info to combat it. I understand that. Yeah, I've definitely been. I mean, I peek my head in every once in a while, but it's definitely not. Uh, it's starting to get old. The derp, definitely. So, what can you do? So, talking about some gravitational potential today. So I have a slightly different setup. So I have my quantum. Let me bring up my gravity textbook, which is to say my classical dynamics textbook. So, boom, awesome. So basically, we're going to chapter 5 of my classical dynamics textbook, and what we're going to do is talk about an interesting thing I found in doing our homework today. So basically, right now I'm taking a relativity course. So I'm about to graduate from my bachelor's degree in physics and my astronomy degree in physics. But for your bachelor's degree in physics, you have to take an upper level course. Well, you have to take several, but you also have to take like one of the highest upper level courses they offer. One of them is Quantum 3. Quantum is not my forte, so uh, I didn't opt to go that route. But I do find relativity interesting, so I signed up for relativity. So that's the course I'm in right now. You could also take solid state physics, which apparently does have to do with quantum. I don't really know exactly what that is. You're looking into it a bit. It didn't really interest me. And you can take electrodynamics too, which I think I could have did all right in. Like I ended up getting A minus in electrodynamics, but that's only because I fought so hard at the end and pulled it up with my final. So that's still not my best subject as well. But I would say classical dynamics is probably my favorite or best so far. And when you get into relativity, uh, a lot of stuff we talk about, I'm learning is also classical dynamics, both to compare the two, and also because, and I haven't learned this directly yet, but my understanding is all of Newton's laws can be derived from like special and general relativity. So just a brief about that. And we have on 1824. So this is going to be gravitational. energy, we're going to talk about a very interesting fact that comes out of this homework. So basically what's happening is special relativity. What I'm learning in my class is basically dealing a lot with time, generally. And general basically also includes space. That's a very rough estimate. And you do talk about uh, space contraction here as well, but it seems to me that general relativity is going to get very much more into the curvature of space-time. That's why I mentioned space in that way. So right now we're talking about special relativity. And one of the things we did was venture back into gravity and gravitational potential. So I'm going to go through a few of these equations here, and then we're going to end up with a very interesting result that my professor that gave me an aha moment when I was in his office asking clarifications for this stuff. So you may be familiar with this equation here. The force of gravity equals negative the gravitational constant m over r squared, and it is a vector, so it has a direction. Certainly. Let me let me do this. So it says let's make the chapter a bit larger. I shall move this over here. Or I can do like this. I can do like that. Welcome. And I shall move this over here. Right? I could move that down some. There we go. There you go. Thanks for letting me know. So I'm glad that's better. Awesome. So ironic. So this is the chapter 5 on gravitation. Introduce Newton's formula. So we have that. And so you have basically the mass of the gravitating object, the mass of the larger gravitational field, let's say the mass of Earth, the distance between them squared, and r. And the focus of this homework problem was to get to the gravitational potential. So if you look at G, G is basically the gravitational force vector. And I love relating this to uh, electrostatics. So you have G here, and I'll put K here for the Coulomb constant. You also have Fk equals K Q1 Q2 over R squared, and that's also a vector. So what happens is if you divide Fk by Q, and I'll just make that one just a regular Q, you end up with K Q1 over R squared R, and that's like the uh, electric field, right? And G has something similar, where if you divide G by M, you get negative G M M oops M over R squared R hat, and that equals G. So just like how electricity has an electric field, gravity has a gravitational force vector, like a force vector that depends only on the mass, the gravitating mass in question. So this should also recall something I covered, I guess a few weeks ago now, whenever, about how when different masses are in a gravitational field, the individual masses cancel because the gravitational force vector is going to be that of the largest object, just like how for the sun, That's going to be the gravitational force vector for the whole solar system, and all the planets are orbiting the sun. On the Earth, the gravitational force vector is going to be by the Earth, and everything else is being attracted to the Earth. So I think that's a very cool parallel. Now, another thing we can do is get something called gravitational potential or gravitational potential energy. And Lisa says we should try to use ChatGPT to equate those two equations to each other to have fun with that. Yeah, I've heard about science deniers doing weird things trying to equate equations. It reminds me of my talk with Ross, but it's sad. Now, interesting thing is G, and now I'll cut that one off there. We'll continue with this. G equals negative the derivative of the gravitational potential. And this is what we want, gravitational potential. So that means that the integral of G equals negative gravitational potential. And so that means that the integral of negative V M E over R squared equals that. So we can go ahead and do that integral and say I equals the integral. We can say Gm, the integral of R negative 2 dr. So that equals Gm, and we have R negative 1 divided by negative 1 plus C, and thus we end up with Gm negative over R, and this C factor is so small we could ignore it. I learned from my professor, because you're dealing with like the mass of the Earth, that little bitty factor there is not really making a difference. I suppose if you're calculating like the precession of Mercury or something, then you'll need that, but we don't need that for our purposes, like dropping a ball from a tower or something. We have this, and there's the equation there. That's where they got that from. So this is the gravitational potential energy, right? So what this is basically referring to is if we have, let's say, the sun here, and you notice that this R is not squared, it's just an R. So that means that at these distances away from the sun, there's a certain gravitational potential energy at that radius. So if this is 1R, this will give us a certain gravitational potential energy. If this is 2R, it'll give us a little bit less, and it's going in a linear fashion. Linearly, we have less gravitational potential energy as we get away from the gravitating body. Now, here's the cool thing. What I'm going to do is I'm going to calculate the gravitational potential. That's right. It decreases with increasing R because it's still related to the force. It's still related to the force. So remember that we got F, we got G, the force vector G, from dividing that single mass of F. And gravity decreases as 1 over R squared. So we can say F is proportional to 1 over R squared. But the gravitational potential energy being negative G M over R, if I wrote it correctly, that falls off proportional to 1 over R. So it has a linear relation, but it does decrease. And thinking about it now, this must have something to do with like Kepler's laws, because Kepler's laws, we have, let me see if I can remember that. That's P squared equals A cubed, where P is the period of planet rotation. and A is the, P is the, P is the period, and A is the semi-major axis. You could basically say well, let me just put semi-major axis, and that's very consistent. So it must have something to do. All of this stuff has to be related because the whole system works together. Even though I haven't explicitly made that connection, but it just comes to mind that this has to be related because we can get our orbit so precisely now. And this has absolutely to do with that, what we're about to do now. So what we're going to do, we're going to calculate and actually let me try something else first. I didn't do this already. Let's see what we get. So let's say we have the orbit of the Earth, right? We have the sun here. We have the Earth here. Um, we have the radius of the Earth. And let me get the radius from the Earth fact. Not the radius, but the you know, orbit. We know it's 1 AU is 93 million miles, but what is it in kilometers? Hmm. Orbit. Let me just search 1 AU in kilometers. 150 million kilometers? That sounds good. Right. So we have 150 million kilometers. 150 million AM. Right? So that's R. And if we want the length of that circle is 2 pi R, there's going to be 2 pi 150 0 0 0 0. So that's going to equal 2 pi times d equals, so that's 9.42 times 10 to the 8 kilometers, right? So we're doing that in a year. So we have 365 days times 24 hours times uh, uh, 60 minutes times 60 seconds, right? 1 year, roughly. I know it's not exactly 365, but it should be good for all purposes. So 365, 24 each of those, 50 each of those hours, and 60 seconds each of those minutes. So that's 3.15 times each of the 7 seconds. So if I was to divide these, let's see what we get. So we get 2.99 times 10 to the 1 kilometers per second, or you can say 29.9 uh, uh, kilometers per second. Now, what we did was we got the speed of the Earth around the sun by direct calculation from the distance to the sun, which we know from bouncing radar off on, and now we even sent a satellite to it, so we know that distance pretty well. Um, we know how long a year takes because I mean we're on the planet. We can see how long the seasons take to come back around. So we have this. Now, watch this. We're going to get the gravitational potential of the Earth at this distance. So again, that's going to be G M uh, uh, sun over R. And how do I write this? Over RAU. That's it. And the mass of the sun. So basically, what we're doing now, by the way, we're getting the gravitational potential of the sun. Like just like how I drew these lines here, we're going to get one of these potential lines. We're going to get this potential line at the orbit of Earth. And we're going to see what it tells us about Earth's orbit from understanding the gravitational potential. So we have, and by the way, let me put these pages in the stream. At least it says that's the angular velocity, not the linear velocity, right? I always get those two mixed up. I'm pretty sure this will be the linear velocity. This will be just the velocity going straight. But I always got those mixed up. I never took the time to really get those worked out really well. But I should know because one of our other homework problems we had to sort of solve for that. But I did an equation slightly differently than the one my professor did, so that's probably why it doesn't stick to mind so much. But I can pull up some notes on that in a bit. But I believe this is angular. But suffice to say, if we were to take a, the Earth was here, and we took like a radar gun right here and put it onto the Earth, we would get 30,000 kilometers a second. I can say that much. If we were like sitting on the side of the road with a radar gun, we would get 29.9, about 30 kilometers per second. Whether it's angular or linear, that's what we would get if we just put a radar gun on it. Now, sounds good, linear. So you always get those mixed up. Now the mass of the sun, that was the Earth fact sheet. I'll get the sun fact one. Right? And I use these pages a lot during my like astronomy classes and stuff because I don't remember these values. So the mass of the sun equals 1988400 times 10 to the 24 kilograms. V equals, and I always go to Britannica to get this. Now, this would actually brought me into my uh, uh, professor's office because the units can be written in so many different ways. And I was like, dude, these units are not matching up. But then it connected something very interesting that we did in class as well. So G is going to be 6.6743 times 10 to the negative 11 meters cubed over kilograms second squared. And the radius, the AU we already got is, RAU is 150 million kilometers. Right, so what I'm going to do is I'm going to plug that in. And we're going to find out I equals, so I'm plugging this in for that, this in for that, this in for that. And if you have a calculator, you should do it as well. We'll find something quite interesting. Right? So what I get is 8.85 times 10 to the 8. And let me put the units here so we can work these units out together. So I have G, that's meters cubed, over kilograms second squared. For mass, I have kilograms. And for the radius, I have 1 over meters. It says kilometers, but I put it in as, let me write that, times 10 to the 3 meters. That's how I typed it in. I added a 10 to the 3 to make that meters, right? So if I was to get the units for this, let's look at this. The kilograms cancel. One of these meters cancels. So that means we get I naught equals 8.85 times 10 to the 8 meters squared over a second squared. So this means that the gravitational potential, the units, this gravitational potential energy, the units is a meter squared per second squared. What do you get if you take the square root of meter squared per second squared? If you have meter squared over second squared, and you take a square root, you get meters per second. So let's see what this is. Let's take the square root of I naught, which is the square root of 8.85 times 10 to the 8 meters squared over second squared. If I take the square root of that, I get 2.97 times 10 to the 4 meters per second, or 29.7 kilometers per second. Mind blown. Mind blown, right? For a slight uh, calculation error, we rounded up some numbers. We didn't use any exact values. But you see that if you look at the planet physically, you look at how far away from the sun, you look at how long it takes the Earth to go around the sun. If you just look at that physically and measure how fast we're going, you get about 30 kilometers per second. If you take gravity, the force of gravity, derive from that the gravitational force vector, integrate to get the gravitational potential energy, calculate the gravitational potential energy of the Earth at that distance from the sun, take the square root, since the units of gravitational potential energy is meters squared over second squared, that gives you velocity. And what do we find? The exact velocity, given our allowable errors of the Earth going around the sun. So it's no surprise that when we physically measure the speed of the Earth, we get about 30 kilometers per second. Is because the way gravity works, at this our distance from the sun, we're at the distance where bodies here have that gravitational potential energy such that they go about 30 kilometers per second. Ain't that something? So I thought this was pretty interesting. My professor thought this was a very interesting fact as well. He didn't bother to calculate the uh, actual, you know, gravity, the speed directly, but figured I would go ahead and do that, which I didn't do before, but it could have came out unexpectedly. But of course, these things have been observed and stuff for so long that we know what they're going to be. But isn't that nice? So just observing the speed of the planet through the solar system and understanding gravity is an interactive confirmation of both. So that's the interesting fact I wanted to show you. I thought that was pretty cool. I thought that's pretty nice that you can take the gravitational potential energy and get the speed of the Earth just as you could by physically calculating the speed of the Earth. It's awesome. Do you have any questions, any comments, Lisa, or anybody else that's watching? Lisa says, I'm quite blown away. I never realized we can know that from another way. It gives another layer of understanding. Nice. Yes, very cool. And that's the interesting thing about science and physics. It goes back to something I heard my thermodynamics professor take, because I'll be talking about thermodynamics as well. If you recall, that's why I prepared for either a debate or talk, whatever on that topic, because I know I'll be studying it this semester. And I was in his office yesterday, and he was talking with another student, and the student was asking to join his research group. He does some complicated stuff, like modeling some complicated stuff. And he said, "Look," he said, "you can't join my group um, because you have to learn more." He said, "Even beginning graduate students can't join my group because you need quantum field theory, I believe he called it. Either gravitational field, you need some kind of field theory. You need some serious stuff to do the stuff he's doing." But he was like, just find a research group that's doing stuff at your level, and you can still learn how to do research. And whatever capacity you learn how to do research, that'll be good when you do get the background to join a group like my group. And I asked him, I said, could you elaborate on what you mean by learn to do research, right? And he said, basically, when you're doing research, he said it's different. Like when you're doing like a homework problem and you have A plus B equals 1, he said what you might do is solve for A, and then when you have A, you can do B equals 1 minus A and get B. But he said with research, you don't do that. He said you solve for A and you solve for B and you figure out if it works. And he said not only do you solve for A and you solve for B, he says you solve for A and B in as many ways as you can. Not just one way, but as many ways as you can, because you could be wrong. But if you solve for it in as many ways as you possibly can, and if they all give you the same answer, then that gives you confirmation. And that's what we did here. So we got the speed of the Earth one way by just looking at the Earth and measuring it, basically. And we also got the speed of the Earth saying, hey, we have this understanding of gravity. Our formulas say gravity does this. Our understanding is that mass always attracts a mass. It always attracts a mass according to this equation. Uh, uh, F equals m over r squared. We know that we have a gravitational vector similar to the electric field. We know we have a gravitational potential energy. So if that's accurate, it should be accurate in this scenario as well. And we calculated it for this scenario, and we got the same answer as we did for simply measuring it. So that's what this is about. So there are, I'm sure, even other ways, because guess what? When I get better at relativity, I should be able to come back and do a relativistic calculation and say, okay, we have general relativity, space time is doing this, and so on and so forth. And I should still be able to get the same speed, albeit a bit more precise, just like how we can get the precession of Mercury. This is a first of thermodynamics. So that way you're confident in your answers. That's correct. And that's how physicists do their research, right? You can't just look at it one way and say, aha, you know, now I know that space time is bending. No, we do it multiple ways, so now we have, uh, uh, we can calculate it. It was the thing with the solar eclipse. Now there's, gravitational waves, of course, that's a big thing. There's Einstein rings and gravitational lensing and so on and so forth. So in every single multiple way, just like how with gravity, you know, uh, this would actually be more of the confirmation for gravity because I mean this is just looking at the planet and just seeing what's going on. Uh, but the fact that we got the same answer with gravity is another confirmation for gravity, along with the Cavendish experiment and finding was it what was it? Finding Neptune from the gravitational perturbation of Uranus, and so on and so forth. All of these things correlate to give us, and that's how things become eventually theories and laws. Not because people just decide that it should be a theory or a law, is because there's so many different ways that these things have been confirmed that, okay, that's a theory, that's something that we know is stable, that's applicable again and again and again in every single scenario. Okay, that's a law. That's something that we know is mathematically applicable. PV equals nRT. You get yourself some ideal gas or something that acts like an ideal gas like air, a relatively stable pressure like 1 atmosphere, PV equals nRT will work again and again and again. It's awesome. So that's all I have for now. I just wanted to get that awesome tidbit in. Thank you for showing up, Lisa. Thanks for everybody else who joined and watched. I hope y'all found that interesting. And I'll go ahead and see if I did this one a bit early to make sure that I could have the stream in case Nicholas did show up. So far, I haven't seen anything of him, but it's still not 8 o'clock yet. So I'll go ahead and log off. And if you don't see me on in a bit with Nick, then you'll see me next week throughout the week. I'm sure I will be here more than once, but at least I'll be here Saturday. You're surely welcome, Lisa. I'm glad I can help you get some kind of intellectual stimulation, a break from the derp. And now you have another interesting fact, another interesting confirmation of gravity, another good thing you could talk about at the coffee table with your friends. Let's check this out, guys. Isn't this cool? So thank y'all for watching. Have a good day.